Okay, shall we start? Can you hear me?
Yes, sir.
Yes,
Okay.
sir.
So just let me know when my screen is visible. Is my screen visible?
Yes, sir.
All right. So in the
Yes, sir.
previous class, we were
Yes,
talking
sir.
about zeros and singularities. The singularities are those points where the function ceases to be analytic. Okay. So types of singularities. I talked about removal singularity. Then I talked about pole. So pole is whenever the Lorentz series it has got a finite number of negative terms. Okay. And finally, we had essential singularities. So those singularities which are neither removable nor they are a pole. Okay. So that is there is exists no finite value of n such that if you take the limit z minus z naught to the power n into f of z, it is finite. Okay. So no such value of n exists to make this limit finite. So this is an example of a essential singularity. Can you identify? Have we done this in the previous class? Did we do this? Has it been done in the previous class? These three problems?
No, sir.
Not
Yes,
done?
sir.
Okay. Yes means it's done or not done?
Not done, sir.
It's not done. Okay. All right. So first one, identify the singularity of the function. Okay. What kind of singularity is this? We have to identify. Okay. Whether it's a pole, whether it's a essential singularity, whether it's a pole or whether it's a removable singularity. That's what we have to identify. Okay. So let me write down the problem here. If you have pen and paper, just note down. Okay. Question number one. I'll show you question number one. Okay. Question number one, I'll show you. If you have pen and paper, please note it down. Okay. So f of z, number one, f of z equals f of z equals e to the power z minus a divided by z minus a square. Okay. Have you noted it down? Because now I'm going to switch to my phone. Okay.
Yes, sir.
Okay. Can you see my phone screen?
Yes, sir.
All right.
Yes, sir.
Is this visible?
Yes, sir.
Okay, so this is f of z equal to e to the power z minus a by z minus a squared. So we need to check what kind of pole is this. So this is really easy. So all you have to do is you take 1 by this 1 by z minus a whole square. You can take it common outside. So 1 by z minus a whole square, you take it outside. And then you just expand this. You just expand this e to the power z minus a. You just expand this because this is the exponential function. So that is easy. So that is 1 plus because e to the power x is e to the power z is e to the power z, right? The Taylor series expansion of this e to the power z, the Taylor series expansion of this is 1 plus z plus z square by 2 factorial plus z cube by 3 factorial and so on, right? So we have to use this expansion. So therefore we have in this case 1 plus z instead of z we'll use z minus a. Okay, then plus z minus a whole square by 2 factorial. Then we have z minus a whole cube by 3 factorial, and so on. Okay, so this is what we have. Now just take this 1 by z minus a whole square, you take it inside, and when I do it, I get 1 by z minus a squared, 1 by this. Then z minus a by z minus a squared, this becomes 1 by z minus a alone. Then z minus a whole square. Okay, just a sec. Z minus a whole square, z minus a whole square will get cancelled out, and so we will have 1 by 2 factorial, 1 by 2 factorial, and then here the power has now become more, so this is going to become z minus a by 3 factorial, and so on. Okay, we are not interested in this part, the positive powers. We are interested in only the negative powers. How many terms are there? How many terms do we have? Number of terms is 2, right? Number of terms is 2. So therefore z naught equals a. Z naught equals a is a pole of order 2. Number of terms is 2, so the order of the pole. Okay, I think we should go to video mode. That's much better. Yeah. So the order of the pole is 2. Okay, because number of terms is 2, order of the pole is 2. Is this clear? So that's how you do problems like this. Fine. Now let's go back to my slides. Let me know if you're able to see my slides.
Yes, sir.
Okay. So you can do it for the others, right? Identify the singularity for this and this. Okay, what kind of singularity do we have? Okay, please try this on your own. All right. Is this clear?
Yes, sir.
Now let us, yeah. Now some properties that you need to remember. Zeros and poles are complementary to each other. So if I have a function f of z which has got a 0 of order m, and then this function, if you just take the inverse of this function 1 by f of z, then in that case what was the 0 for this function will become the pole for this function. Okay, whatever was 0 for the function f of z, for this inverse function, that same what was 0, it will become a pole of the same order. If it's order 2, then it will become a pole of order 2, and vice versa. Okay, so zeros and poles, they have this complementary behavior. Then if a function f of z has a 0 of order m at z naught, okay, where g of z, some other function g of z has a pole of the same order, then that is basically, suppose I have a function f of z at z naught. This function f of z has got a 0 of order m, and some other function g of z at the same point has got a pole of the same order m. Then if I multiply these two functions f of z and g of z, then the product of these two functions is either analytic at z naught, or it has got a removable singularity there. Okay, important properties to remember. These are basically to help you solve problems for the net exam. Okay, to quickly solve problems. Then we have something called as the argument theorem. If function is a function f of z is analytic inside and on a simple closed curve except for a finite number of poles inside, then if you're asked to evaluate this one, then this will be simply n minus p, where n and p are the total number of zeros or poles. Okay, n and p are the total number of zeros, n is the total number of zeros, and p is the total number of poles inside C. Okay, counting multiplicities. Okay, it's like, for example, if I have z minus a whole square, so a could be a 0 or it could be a pole, so you have to, because it's squared, so that means you have to count it 2 times. Okay, so that's the argument theorem. Okay, I'll not go more into the details of this argument theorem. We are interested in residues because that is going to help us solve many real integrals. Okay, so what is a residue? A Lorentz series expansion is this. Okay, so this is a Lorentz series expansion. Now if I perform a term by term integration in equation number 1, that is, you integrate this one, you integrate the left hand side you integrate over some contour C, the right hand side also you integrate over some contour C. Okay, so now what we do is we bring this inside. Okay, this I can take this integration inside, so I have the summation which goes outside and an also comes outside, and then we have this. Now do you remember this integration of z minus z naught to the power n? We had done a result, right? Do you remember?
Yes, sir.
Okay, what was the result? Can you see my phone screen?
Yes, sir.
This was the result, right? Suppose I have any contour C. If I have any contour C, then integration over this contour z minus z naught to the power n dz. What is this equal to? It is equal to twice pi I if n is equal to minus 1. If n is equal to minus 1, it is equal to twice pi I. And if n is not equal to minus 1, then what's the result? What's
0.
the result? It will be 0. Remember this result? So we can make use of this result here. Okay, we can make use of this result here. So what did we have? We had something like this: summation n equals minus infinity till plus infinity an integration c z minus z naught whole to the power n into dz. This is what we had. So then you could just do expand this summation. So what will happen is, only for n equals minus 1, only for n equals minus 1, this will be non-zero. For all other values, this will become 0. This integral will give us 0 as per this result. For whenever n is not equal to minus 1, this will be 0. Only if n is equal to minus 1, this will be non-zero. So out of this entire summation, only n equal to minus 1 is going to survive. So as a result, so we will only have one term left. This will be the last man standing. N equal to minus 1, and the result of this will be 2 pi I. This is going to be the result. So this is what we have used over here. Okay, this is what we have used in this case. Okay, let me switch back. All right, so because of this, we have this left hand side. This is equal to twice pi I into a minus 1. You see, lots of coefficients are there. The a minus 1 coefficient, the coefficient which corresponds to the n equal to minus 1, that is the only coefficient that is going to survive over here, and we have this. Okay, so as a result of this, this is known as the residue a minus 1. This a minus 1 coefficient in the Lorentz series expansion, we have a Lorentz series expansion. In the Lorentz series expansion, this a minus 1 coefficient, that is known as the residue. Okay, in other words, this is what we have. Can you see my phone screen again?
Yes, sir.
Okay, so we have the Lorentz series. Okay, so there's the Lorentz series. So now the Lorentz series, I would like to write down how do you write down the Lorentz series? So we have the positive part and the negative part. So we have a0, then we have a1 into z minus z naught plus a2 z minus z naught squared, and so on. And on this side, we have the negative powers. That is, a minus 1 will be there divided by z minus z naught. Then we have a minus 2 divided by z minus z naught squared, and so on. Right? This is the Lorentz series. Now what we mean by this is this quantity. Okay, this coefficient, write down the Lorentz series. This coefficient that you have, This is known as the residue. Okay, this is known as the residue. Is this clear to everyone?
Yes, sir.
Okay. So if you are asked to find out the residue, all you need to do is write down the Lorentz series expansion, and in the Lorentz series expansion, find out that term which is 1 by z minus z naught, that term. Whatever is the coefficient of that term, that is the residue. Fine. All right. So now, how do you find out the residue? Okay, there are two different formulas. One is the residue at a simple pole. At a simple pole, this is the formula. The residue, finding the residue is you just multiply f of z with z minus z naught. Okay, just multiply f of z with z minus z naught, and then all you need to do is just take the limit as z tends to z naught. So that is the first formula. Second formula is if this function f of z can be written in this way. Okay, in this way as a quotient of two functions p of z and q of z, where p of z naught is non-zero and q of z has got a simple zero at z naught, that is a zero of order 1 at z naught, then f of z has a simple pole at z naught. Okay, so we are so this is how we can obtain this. So in that case, this is going to be the residue is simply p at z naught divided by the derivative of q evaluated at z naught. So that is going to give us the residue. We're going to use this one. This is for a simple pole. Okay, this is the easiest one to use. And as an example, we need to find out the residue of this using both the above formula. I leave this to you because I'm going to do some other examples. So I'll leave this to you to just try it out on your own. Okay, we'll do some other problems. Then if I want to find out the pole of any order, okay, if I want to find a pole of any order m, okay, this, by the way, this is very straightforward. Okay, you can just use either of these. All you have to do is z naught equal to I. So first you try z minus z naught, that is z minus I. Z minus I, you multiply this one, see if you can and then you substitute z equals z naught. Take the limit as z tends to z naught. Whatever you get, that is going to be the residue. That is one way. That's the first formula. Second formula is you identify it. What is in this case p by q? So which is p is equal to 9z plus I, which is q, z into z square plus 1, that is q. Then take q, you differentiate it. Okay, q prime you differentiate it, and then p you substitute z naught, and q prime you also substitute z naught, and then find out what is the value. You should get the same residue using both the formula. You should get. Okay, so I really encourage you to try this out on your own. All right. Now, for pole of any order, instead of simple pole, if I have a pole of order m, where m is greater than 1, okay, so in that case, okay, so what you do is this function f of z, you multiply with z minus z naught to the power m, then this is going to become z minus z naught. Already there was z minus z naught to the power n. Now, since I'm multiplying z minus z naught to the power m, so this m will also get added over here. This is going to be analytic because that's the definition of a pole, right? From the definition of a pole, if I have a pole of order m, then if I multiply this function with z minus z naught to the power m, either it becomes analytic or it becomes removable. Remember, we had this, right? This property, right? If a function has a zero of sorry, not here, just one second. I'll find this, just a second. Okay. Just give me one moment. Okay, I'm getting a phone call. Okay, we'll just carry on from here. Okay, so this is going to be analytic. You multiply z minus z naught to the power m, and I multiply with this. This is the basic property of a pole of order m. This is going to be analytic. Multiplying this is going to be analytic. Now, if I differentiate this m minus 1 terms, this is what I'll get. Okay, then the formula for finding the residue, okay, for a pole of order m at z naught. This is the formula: 1 by m minus 1 factorial, taking the limit of the derivative, the m minus 1 derivative of z minus z naught to the power m multiplied with f of z. So this is the formula for the order of a pole of any order at z naught. Okay, so this is the formula. Let's and there is one more concept which is called as residue at infinity. I'm just giving you the formula. A function, if you're asked to find out the residue at infinity, all you have to do is find out the a minus 1 coefficient. Negative of that, that is known as the residue at infinity. Such problems, they come very frequently in net exam, so that's why I'm just given this over here. Let's take this case. Okay, we need to find out the residue of f of z. We need to find out the residue of f of z equal to z cos 1 by z. Okay, the first problem at z naught equal to 0. So this is what we need to find out: the residue at z naught of this function at z naught equal to 0. So let me just share my phone screen again. Are you able to see? Is my screen visible?
Yes, sir.
Yes,
Phone
sir.
screen? All right. So we need to find out the residue of this function f of z equals z cos 1 by z. We need to find this at z naught equals 0. So this is what we need to find out. This is very straightforward, because this f of z, okay, I take the z outside and then you just expand this cos of 1 by z. So what is the expansion of the cos function? Cos of z, what is the expansion? Cos will contain all odd terms, right? Alternating plus and minus sign. So it means cos of z will be 1 minus z square by 2 factorial plus z to the power 4 by 4 factorial minus z to the power 6 by 6 factorial plus minus and so on, right? So this is the cos, right? So you just replace this over here. Only thing is, because this is not cos of z, this is cos of 1 by z. So we have to replace this z with 1 by z. Okay. So as a result, this is going to become 1 minus, instead of z square, it will become 1 by z square. That is 1 by 2 factorial into z square plus z to the power 4. Instead of that, it will become 1 by z to the power 4. So 1 by 4 factorial into z to the power 4 plus, sorry, next we'll have minus. Then we have z to the power 6. So this is going to become 1 by 6 factorial into z to the power 6 plus minus and so on. Okay, now we just need to multiply this z everywhere inside, and as a result, we will get z minus, then this z, one of these z will get cancelled, so we'll get 1 by 2 factorial into z, okay, then plus 1 by 4 factorial, z to the power 4 and z will get cancelled, we'll get z cube here, so minus 1 by 6 factorial, z to the power 6 is here, 1, this power will go down by 1, so we'll have z to the power 5 plus minus and so on. Now how do you identify the residue? How we identify the residue is, look for that 1 by z minus z naught term. 1 by z minus z naught term. Which is the 1 by z minus z naught term? This is the 1 by z minus z naught term. It is the 1 by z minus z naught term. That means whatever is left, whatever is the coefficient, this must be the residue. This must be the residue. Understood? So therefore, the residue, okay, we write it like this: the residue at z naught equal to 0, the residue at z naught equal to 0 of the function, which is the function? The function is z cos 1 by z. This residue is equal to minus 1 by 2 factorial, which is minus 1 by 2, minus half. That's the residue. Is this clear? Is this been understood by everyone?
Yes, sir.
Please try
Yes,
this.
sir.
Try this problem number 2. Okay, z cube by z square minus 1. Try this out. Okay, just try it out. Residue at infinity. So here again, all you have to do is find out the Lorentz series expansion, and in that Lorentz series expansion, find out what is the a minus 1 coefficient. Moment you get a minus 1 coefficient, residue at infinity is minus a minus 1. So just put a negative sign on it. That's going to be the residue at infinity. Then let me do one more problem where, let's see. Yeah, let me try the third one. Okay, problem number 3. Just give me a second. Let me write it down. Write down the problem. You all also can write down on paper. Problem number 3. Problem number 3. Question number 3. The function is f of z equals 1 minus twice z divided by z into z minus 1 z minus 2. Okay, so that's the function. All right, so let me show you how to do this problem. We have to find all the poles and the corresponding, we have to find all the poles and the corresponding residues, the poles, the residues corresponding to each and every pole. Remember, every pole will have its own residue. Okay, so this is the problem. Can you see?
Yes, sir.
So here we need to first find out the poles, right? So what are the poles here? Okay, what are the poles? So here we have 3 poles. Poles are those points where the function is going to become undefined, or just look for points where the denominator becomes 0. So it means z minus 1, write down the denominator, z minus 1, z minus 2. The entire thing, wherever it becomes 0, that's where those are the poles, right? And the moment you do that, from here we find out what are the possibilities. The one possibility is z equal to 0. There is one possibility. Another possibility is z minus 1, right? Z minus 1. One is z equal to 0. Another one is z minus 1 equal to 0, which implies that z is equal to 1. Z equal to 1 is another possibility. Then one more possibility is z minus 2 is equal to 0, which implies z is equal to 2. So therefore, and what are the powers? What are the powers? The power is 1 here, 1, 1 and 1. So we have simple poles here. Simple poles. Simple poles, there is m is equal to 1. M is equal to 1 at z naught equal to 0, 1 and 2. At z naught equal to 0, 1 and 2. Is that clear? Now for simple pole, what is the formula for the residue? We'll use the first formula, the residue for a simple pole. The residue at z equals, at z tending to z naught, the residue of a, or rather I should be writing like this. This is not the way. Residue at z naught for a function f of z. What is the formula? The formula is you multiply the function with z minus z naught. Multiply the function with z minus z naught. Okay, and then take the limit as z tends to z naught. Okay, so this is the formula, and this is the same formula that we'll be using in this case. So for the pole z naught equal to 0, for the pole z naught equal to 0, what is the residue? What is the residue at z naught equal to 0? what is the residue at z not equal to 0 for the same function f of z. All you have to do is just use this formula. So we have limit z tends to z naught is 0, z minus z naught, z minus 0 names the function f of z, so which is equal to limit z tends to 0, z minus z naught is z, and now write down the function f of z, which is the function is 1 minus twice z divided by z into z minus 1, z minus 2. That's the function. And then over here, this z and this z will get cancelled out. So what is left behind is, now you can just substitute 0 here, doesn't matter, because this would have given problems. Now you can just substitute 0 everywhere, and this is going to give us 1 minus 0 divided by 0 minus 1, 0 minus 2. So this is going to give us 1 divided by minus 1 into minus 2, which is going to give us 1 by 2. So 1 by 2 is the residue corresponding to z not equal to 0. Similarly, please find out what is the residue for z not equals to 1. Okay, I'll leave this to you. Let's try this out and find out what is the residue for z not equals to 2. Let's find that out. Okay, I'll give you the answer so that you all can verify. You should get this to be equal to 1 and this to be equal to minus 3 by 2. Okay, so please try this out. Is that clear?
Okay, sir.
All right, let me go back to my slides. Okay, so in the same way, you can work out for the others also. That is for question number 2, 4, and 5. Please try this out. Okay. Question number 5 is a little bit interesting. Okay, find the residues of f sine z by z cos z at its poles inside modulus z equal to 0. Modulus z equal to 0, it's a circle. It's a circle of radius 2, which is centered at the origin. Okay, the fifth problem. This is a circle. So we have to consider the poles. So you know what is sine and you know what is cos. So all you need to do is find out, because find out what are the, for what values of z will z cos z will it become 0. Those are going to be the poles. Okay, is z equal to 0, obviously that's a pole. But when does cos of z, for what values does this become 0? So that you find out. And then out of these, which of these lie inside this circle? Okay, that's what you need to find out. Then only those poles you will consider. So only 3 poles you'll have to consider. 3, yeah, only 3 poles you'll have to consider. So can you work this out on your own? Just try it out. Okay, it's an interesting problem. Okay, try this out. Okay, so that's finding the residues. Then we have something called as the residue theorem. Let me just stop for the time being, or maybe I think I can continue with the residue theorem. Yeah, residue theorem is, I don't have to, we don't have to know the proof of the residue theorem. You just need to know how to apply the residue theorem. So let's do the residue theorem and we will stop here for today. Okay, so the residue theorem. What does the residue theorem say? It says that if a function f of z is analytic on a simple closed curve, so I have a simple closed curve C, and I have a function which is analytic over this simple closed curve, and there are some singularities z1, z2, and so on inside this, then the value of this integral over the simple closed curve will be simply twice by I times the sum of all the residues. So if I have got the singularities z1, z2, all of them are singularities, then for each of the singularities you'll get one residue. Find out the residues for each of these singularities and just add them together. That sum you multiply it with twice by I. So that is going to be the value of this integral. So let's do a problem, then it's going to become clear. The problem is here z square, okay, the first one z square dz divided by z minus 1 whole square divided into z plus 2. So let me do this problem. Okay, can you see my screen?
Yes, sir.
All right, so this is what we need to do. Okay, so here we have the integral that we are considering. The integral is, let me write this down. This is z square dz divided by z minus 1 whole squared z plus 2. Okay, and over here c is the contour such that modulus z is equal to 3. Okay, so we are considering a circle. We are considering a circle of radius 3 which is centered at the origin. Okay, so this is what we are considering. So we're considering a circle, and the radius of the circle, the radius, this is 3, the center is 0 and the radius is 3. So now over here, what are the poles? Immediately you can identify. If you put z equal to 1, this is going to become infinity. So we have one pole is z not equal to 1. Z not equal to 1 is a pole, right? Put 1 here, 1 minus 1 is 0, so it becomes undefined. What is the order of this pole? Look at the power. Okay, what is the power? The power is 2, so order is 2. Then we have another pole. You put z equal to minus 2. Okay, you put equal z equal to minus, so this becomes 0. And what is the order of this? This one's power is 1, so order of this is 1. Is that clear, everyone?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so we are going to use the other formula. Okay, this pole of any order. Okay, so that's what we're going to use, right? So I think the formula, let me just get it on the screen. This one, okay, this formula is what I'm going to use. The residue, the last one, the pole of any order m. So this is what I'm going to use. Okay, so let me just copy this down over here. Residue z naught f of z is equal to 1 by m minus 1 factorial. This is important, never forget that. Limit as z tends to 0, d m minus 1th derivative by dz m minus 1 of z minus z naught to the power m f of z. Okay, so this is the formula. I've just noted this down over here. So for the first one, we need to find out for z naught equals 1. For z naught equals 1, we need to find out this residue. The residue at z naught equals 1. Okay, the residue of this function. What is this equal to? So by applying this formula, m is equal to 1, right? So just apply m equal to 1. So 1 by 1 minus 1 factorial. So 1 by 1 minus 1 factorial is 0, right? Sorry, this is m is equal to 2. Sorry, m is equal to 2. So 1 by 1 minus 1, 2 minus 1 is 1. So 1 by 1 factorial, 1 by 1 factorial. Then limit as z naught tends to, as z tends to, limit as z tends to 1, as z tends to 1. Then which derivative? M is 2. So 2 minus 1 is 1, the first derivative. So we are talking about the first derivative. The first derivative of this function, that is z minus z naught, z minus z naught is equal to 1 raised to the power of m, raised to the power of m. M is 2, z minus 1 squared, z minus 1 squared, multiplied with the function itself, multiplied with the function f of z itself. So we write down the function, which is z squared divided by z minus 1 squared z plus 2. This is what we have, right? I just wrote down this function right here. So now this will get cancelled. This gets cancelled out. So this outside, it is all 1. Okay, so limit as z tends to 1, d by dz, we have to differentiate this function, that is z squared divided by z plus 2. This is what we have to do. You can evaluate this on your own. You can use the quotient rule. Okay, you can use the quotient rule. I'll just skip the steps. You can try it out on your own. Use the quotient rule to differentiate this, And when you put the limit here, you should get the answer to be 5/9. Okay, so please try this out. Okay, this in between steps, please try this out. Okay, the steps in between, please try this out. This is the residue for this one. So therefore we say that the residue at z naught equal to 1 for the function f of z is 5/9. Then for the other pole, that is for z naught equals -2. For z naught equal to -2, I need to find out the residue at z naught equals to -2 of the same function f of z. Now this is easy because this is order 1, right? This is of order 1. So you just use the formula number 1, limit as z naught tends to -1, limit as z naught tends to -1, z minus z naught, z minus -2 is z plus 2 times the function itself. The function is z square divided by z minus 1 z plus 2. This will get cancelled. Now all you can do is you can just substitute 1 directly here, and this is going to give us the result. We'll get 4/9. Okay, so this is what you'll get. You should get 4/9. Okay, this also please verify for yourself. So therefore by the residue theorem, we have, by the residue theorem, what does the residue theorem say? This is what the residue theorem, this is what it says. All I need to do is add up. Okay, what does this mean? It means you need to add up all the residues, and that sum of residues multiply with twice by I. That's all we need to do. So by this residue theorem, we have the integration over C of this function z squared dz divided by z minus 1 squared by into z plus 2. This is going to be equal to, as per this, 2 pi I. So 2 pi into I times the summation of all the residues. So summation of all the residues. What are the residues? One is 5/9, another one is 4/9. So we have 5/9 plus 4/9. 5/9 plus 4/9 will give us 9/9, which is going to be equal to 1. And this answer is going to be equal to twice by I. So that's the answer. So that's your residue theorem. Is this clear?
Yes, sir.
Okay, so I think I'm going to stop here. I did one problem. Please try out the other problem on your own. All the problems which we have discussed over here, please do it on your own. I'll share the slides a little later on. I'll provide you with the recording links from the previous class as well as this one. Because the problems are there on the slide, so what I suggest is in the recordings you just pause that on wherever the problem is coming, you pause it there and you note it down. Okay, because the slides I'll be providing in tomorrow's class. So meanwhile you do this problem. All right, then we have the last topic, which is evaluation of real integrals. We'll do that in tomorrow's class. Two different kind of integrals we will see, and that will complete this particular module on complex analysis. Fine. Any questions?
No, sir.
No, sir.
All right. So I think we'll stop here. So tomorrow also same class.